a 2-ton car, 0 to 60 in under 2 seconds. At 20,000 RPM, the rotor is so fast the centrifugal force alone wants to tear it apart. No supercore, no racetrack, a family sedan you can order online right now. For decades, every engineer in this industry agreed, you cannot have this, fast or efficient, power or range. Pick one. Physics does not negotiate. Tesla built an engine that does both. And the way they did it, nobody saw coming. For most of the past 2 decades, the electric vehicle conversation had one dominant storyline. The legacy giants would eventually wake up, flex their manufacturing muscle, and reclaim the road from the upstart in California. And for a while, the evidence supported that narrative. Ford, General Motors, Toyota, Volkswagen. These were companies with century-old supply chains, armies of engineers, and production networks spanning every continent. Tesla, by contrast, was burning cash, missing deadlines, and running a factory described by its own CEO as production hell. The smart money said the window would close, the giants would absorb the lesson, deploy their capital, and the startup would fade into a footnote. Then something shifted. Not a design reveal, not a new color option or a larger battery pack. An engine. When teardown specialist Sandy Munro cut open Tesla's latest drive unit on his workbench, he went quiet at a specific detail. Something wound tightly around the rotor at the motor's spinning core. What he found forced a realization that spread fast through engineering circles. Tesla had not simply improved its motor. It had crossed into territory most competitors could not currently reach. But to understand why that moment mattered, you first have to understand the pressure Tesla was operating under when it happened. The Cybertruck, once Tesla's loudest statement about reinventing the American road, had become a quiet embarrassment. Sales fell well below projections. Reports surfaced that nearly 1 in 5 registrations in a single quarter went to companies directly connected to Elon Musk, including SpaceX and the AI venture xAI. Recalls eroded public confidence. In a market suddenly filled with credible electric alternatives, Tesla's flagship product was not carrying its weight. A company built on the idea of inevitability had started to look uncertain. What was needed was not a refresh. It was something fundamental, the kind of advance that rewrites what is possible rather than simply what is fashionable. The answer was already taking shape inside a quiet engineering bay, far from the headlines. Here is the hard truth about electric motor engineering that most people never hear. Physics is brutal, and for years, the entire industry had simply surrendered to it. Every electric vehicle manufacturer on the planet was working inside the same painful trade-off. Build a motor for raw power and performance, and it runs hot, grows heavy, wastes enormous amounts of energy, and demands complex cooling systems just to survive normal operation. Build it for efficiency and long range, and it delivers a driving experience that feels tame, restrained, incapable of producing the kind of acceleration that makes a driver feel anything, fast or efficient. Pick one. Engineers in meeting rooms across Detroit, Stuttgart, and Tokyo treated this as settled science. The physics had drawn a line. Responsible optimization happened inside that line. Pushing against it was considered naive. The core problem sits inside the rotor, the spinning component at the heart of every electric motor. As rotational speed increases, the forces acting on that rotor grow exponentially. The faster it spins, the more it behaves as though it is trying to tear itself apart from the inside out. Traditional rotor materials warp under that stress. They shed fragments, they overheat, they fail. So the industry set practical speed limits and engineered carefully around them. Conventional electric motors in production vehicles typically operate in the range of 10,000 to 14,000 RPM. That ceiling defined what was achievable in terms of power density, thermal management, and ultimately, cost. And then there was a secondary problem nobody liked talking about openly: heat loss. In a conventional electric motor, a significant percentage of the energy drawn from the battery never becomes forward motion. It bleeds away as heat, vibration, and noise. Engineers compensated with larger battery packs, heavier cooling hardware, and additional complexity, all of which added cost, weight, and new failure points. The industry called this progress. Iterating inside a framework everyone privately acknowledged was fundamentally limited. Tesla decided the framework itself was the problem. The solution Tesla arrived at sounds deceptively simple. Wrap the rotor in carbon fiber. Carbon fiber is a material the aerospace and motorsport industries have relied on for decades precisely because it delivers something that seems contradictory: exceptional structural strength at minimal weight. In Formula One and commercial aviation, It absorbs punishment that would destroy conventional metals while adding almost nothing to the overall mass of the structure. Tesla's engineers applied that principle directly to the rotor. The carbon fiber wrapping functions like precision armor, holding the rotor together under centrifugal forces that would cause conventional designs to expand, warp, and ultimately disintegrate at speed. The results are difficult to overstate. This carbon sleeve drive unit spins at more than 20,000 revolutions per minute. That number almost never appears in the context of passenger vehicles. Speeds that high belong to specialized industrial turbines and aerospace components, not sedans parked in suburban driveways. Yet here it is, inside a car you can configure online in under 10 minutes. But raw rotational speed was never the real story. What made this design revolutionary was the stability it maintained at those extremes. The carbon sleeve eliminated the vibration and microflex that conventional rotors experience under high-speed operation. A rotor that stays perfectly balanced at 20,000 RPM maintains sharper magnetic alignment. And sharper magnetic alignment means more of the electrical energy leaving the battery becomes actual forward motion rather than heat. The efficiency gains cascade from that single improvement. Less heat generated means smaller, lighter cooling systems. Smaller cooling systems mean less weight and freed physical space. Less wasted energy means longer range from the same battery capacity. Tighter magnetic efficiency means sharper torque response. The downstream effects compound across the entire vehicle. The Tesla Model S Plaid demonstrated what this looks like at full deployment. 3 carbon-sleeved motors producing over 1,000 horsepower reaching 60 miles per hour in under 2 seconds, in a luxury sedan capable of carrying 5 passengers and covering hundreds of miles on a single charge. Hypercars costing 10 times the price run slower. The cost arithmetic matters equally. Tesla has engineered this drive unit toward a production target of approximately $1,000 per unit, covering the motor, power electronics, and gearbox. Comparable systems at rival manufacturers cost between $3,000 and $5,000. Multiply that gap across hundreds of thousands of vehicles annually, and the margin difference quietly funds entire new product lines, while competitors are still calculating their losses. Manufacturing this motor at scale is genuinely dangerous territory for anyone attempting to replicate it. Carbon fiber rotor wrapping requires pre-impregnated tape wound under precise, unwavering tension, then cured under controlled heat and pressure until it forms a single rigid shell. Too loose, the rotor fails at speed. Too tight, the fibers fracture. Miss the temperature curve during curing, the entire component is scrap. Every finished rotor then requires dynamic balancing to tolerances that most conventional motor factories never encounter, because a microscopic imbalance invisible at normal speeds becomes a catastrophic, self-amplifying vibration at 20,000 RPM. A competitor cannot photograph the component and reproduce it. They must rebuild the entire manufacturing process around it, line by line, failed rotor by failed rotor, absorbing the full cost of every lesson Tesla paid for years ago. The evidence of that difficulty is visible in the broader industry. Ford lost staggering sums on its electric vehicle division despite building genuinely capable products. Lucid burned through capital. Rivian could not bring production costs under control. General Motors and Volkswagen hit delays, software failures, and deepening profitability concerns. Only BD demonstrates comparable scale, but BD's competitive advantage rests primarily on price accessibility, not technological density. Tesla is pursuing something harder: vehicles that are simultaneously the most technologically advanced, the most aspirationally desirable, and the cheapest to produce at scale. That combination is nearly impossible to replicate by purchasing components from suppliers. It requires owning the entire system. The carbon-sleeved rotor is not a feature, it is a doorway. Through it walks every other advantage Tesla has assembled. The data collected from millions of vehicles on real roads, the 4680 battery cells designed in-house, the Dojo supercomputer processing that data into intelligence, the supercharger network that competitors now pay to access, the software architecture that allowed Tesla to adapt when global semiconductor shortages paralyzed the rest of the industry. Every layer of that system traces back to the same spinning component that stopped Sandy Munro at his workbench. The executives at Ford, Toyota, Volkswagen, and GM who fully understand the teardown report are not worried about losing a product comparison. They are worried about something larger that they are behind on the foundation every future product will be built on. And by the time a rival arrives at that foundation, the target has already moved again.